Hi there folks, and welcome back. Gary Simmons here. Now, after a slight diversion where we looked at pathfinding systems from a high level and also took a closer look at the A-star search algorithm, we're finally back in the project that we created in video 2, and we've got quite a bit slated for this lesson. Firstly, we're going to import some test geometry that I've prepared for you that we can then use to perform our pathfinding tests. We're also going to see what's involved in baking a navigation mesh. We're going to talk about the various settings and how they influence navigation mesh creation, as well as talk very briefly about how navigation meshes are built behind the scenes and what that means to us. We're also going to lay down some waypoints that our agents can follow in sequence, forming a kind of waypoint network. And we're going to write an editor script for that waypoint network so that the waypoints show up more informatively in the scene view so we can see where our agent is supposed to be heading. We're also going to write our very first pathfinding behavior. This is going to be a script of our own creation that is going to interface with Unity's NavMesh agent component to get that agent to do our bidding. In our case, that means get our agent to traverse the waypoints that we've laid down for it. And finally, if we have time in this video, we're also going to examine Unity's navigation obstacles. This is how we deal with dynamic objects at runtime, objects that can't be baked into the navigation mesh. But on that latter point, it may be that we run out of time and we have to push that into the next lesson. But either way, some pretty cool stuff to be getting on with. Now, before we continue, let me just address the issue of all these various tabs I have open in my project that you may not have. Unity remembers all of the windows and tabs that you've set up on a previous session, so you probably haven't got your animator tab up here and 2 project tabs and a lighting tab. So what I'm going to do, just so that we're all kind of on the same page, is I'm going to close down these tabs so that my Unity probably looks a lot more like yours. And then I can open up these windows as and when we need them, and then you can follow along with me. Okay, so remember, with the windows in Unity, you can drag and dock them wherever you want. I think by default, the scene view and the game view actually share the same space. I like to have the hierarchy view on the left, my inspector on the right, my project view down the bottom, and I also like to drag my game view down and dock it next to the project view. Sometimes I like to be able to see the game view and the scene view together. Now, if you ever want to open up a window that you haven't currently got open, you can do this from the window menu, and that shows all of the various windows that you can open up. And one of the windows I like to have up, for obvious reasons, is the console window, because this is the one that tells me all of my errors and any warnings and stuff like that. And I don't like to have it floating. I like to dock that next to the inspector so that I can just flick between the two after I've executed my program. The next thing I'm going to do is I'm going to call up the lighting tab. Okay, the lighting window. Once again, go to the Windows menu, choose lighting, because I want to turn off pre-computed real-time GI and baked GI, because by default now in Unity 5 there's all this computation of real-time light maps going on behind the scenes, and we just don't need that sort of visual fidelity for this demo, and it's going to make things more responsive if I turn that off. And I'm also going to turn down, the ambient intensity, which is right up at 1 at the moment. I'll turn it down to something like 0.1, just so that when we load our scene in, it's not too whited out. And the reason I do this is because the scene that I'm going to load in is something that I've taken from a Unity 4 demo that is available on Unity Technologies' website. It's called the Stealth Project, and it's an excellent example for us to use for pathfinding, but it is using all of the legacy shaders, so we don't really want to be using Unity's new sort of lighting parameters that don't really interface that well with the legacy shaders. Okay, so next up, it's time to import that geometry that I've prepared for you. Now, you'll find if you go to the resources page of the Dead Earth channel, you'll see that there's a zip file in there called Navigation and Pathfinding III.zip. I want you to download that zip file, and in particular I want you to drag out of that zip file the Unity package which is called Navigation and Pathfinding Part 3. Here's the package, I've unzipped it here, and then what I want you to do with Unity open is just double click on that package so that it imports into Unity. You'll see this dialog comes up with a list of all of the assets contained in that package. Just make sure they're all ticked, which they should be by default, and then click import, and those assets will begin importing. And I'll pause the video while that's happening. Okay, so once imported, you'll notice there's a new folder in your project view called Navigation Example. Okay, and if you open that up, you'll see there's two folders in there. Now the first one is called Gizmos, and it contains a bitmap image of a little flag, something I also got from Unity Technologies website. Now this navigation example is something that we're only going to want in our project temporarily when we're doing our pathfinding tests. So we're going to kind of delete all of this stuff down the line. But this Gizmos folder, which contains this flag, I want to keep that because it's these little flags that are going to show up in the scene view for our waypoints. So because we want to keep this, but we will eventually be deleting the navigation example, I want you to drag that Gizmos folder out of the navigation examples folder and drop it in the dead earth folder, okay? So that it's going to remain when we delete the navigation example. Now the next thing I want you to do is I want you to delete the main camera and the directional light from the current scene that is open in Unity, which is just, you know, the default empty scene. Because I've prepared in the navigation example folder a prefab that we can simply drag and drop into our scene, and underneath the parent of that prefab it also contains a directional light and the main camera, so it's everything that we need for testing our pathfinding. So there's the scene, that's what it should look like at the moment. So because we've now got this scene how we want it, let's save it off. So I'm going to go to the File menu, I'm going to choose Save Scene, and I'm going to save this scene, once again, because it's only a temporary scene, not one that we really want to keep around long term, is I'm going to save it in the Navigation Example folder, and I'm going to call it Navigation Example. Why not? And we can now see, if we look in the project view, if you have navigation example folder selected, you'll see that we now have that navigation example scene next to our navigation example geometry. So the first thing we're going to try and do is we're going to try and bake a navigation mesh for this scene as it is at the moment, and just see what happens. Now I'll warn you, it's not going to be very impressive. So let's go to the window menu, and from the window menu we're going to choose navigation. This will bring up the navigation window. Now as you can see, my navigation window is docked on the right hand side of the screen. Yours may pop up somewhere different. Either way though, I actually want my navigation window to be docked over on the left hand side of the screen, sharing window space with the hierarchy tab. And the reasons for this will become clear later on, but I'd just like to be able to select the navigation window and have the inspector window sort of having focus at the same time so I can see them both. Okay, so if we look at the navigation window, we can see it has three subtabs. It has the Object tab, the Bake tab, and the Areas tab. The Areas tab allows us to define different areas by name and assign costs to them. And you'll see later on that these costs are almost like the G cost multipliers that we saw when we were looking at A* in the last lesson. And when we create areas as having different costs, we can then, via the Object tab, select an object in the scene and assign them a certain area, so that when the navigation mesh is compiled, any polygons that were part of that object that got incorporated into the navigation mesh will have the cost of the area that was assigned to it. But we'll see this in action in a moment. Finally, we have the Bake tab, which in many ways is the most important one, as it contains all of the settings that influence the navigation mesh that will be baked. And of course, it also has this Bake button that we're going to press to actually bake the navigation mesh and start that compilation process happening. So I'll tell you what, why don't we press that Bake button and see what happens? Absolutely nothing. Why is that? Well, the reason nothing happened when we tried to bake our navigation mesh is that all of the objects in the scene currently are not marked as being navigation static. Essentially, the navigation mesh generation process sees them as being dynamic objects, and therefore their polygons should not be incorporated into nav mesh generation. So we're going to need to change that, and we're going to need to examine the scene and determine exactly which objects should be part of the navigation mesh process and which ones shouldn't be. So if we go back to the hierarchy, drop down the navigation example geometry prefab, we can see that all of the various objects have been parented and grouped by the type of object that they are. So if I select the debris subgame object, for example, and zoom in on the scene, we can see this contains all of the things like the pallets, the sacks, the boxes, all things like that. Now these are definitely things that we shouldn't be able to walk through. You know, these are solid objects, so I'm going to make these objects navigation static. Now if you just want to make it navigation static, you just go over here on the right with the game object selected, pull down the little drop down, and you can just select navigation static like so, and then it will ask you if you wish to apply this change to all of its children. And we do in this particular case, because all of the children that are under that debris parent are all of the actual debris game objects that we wish to be made navigation static. Now another way that you can do this is simply, let me just reset that. Okay, so if I go up and just click the tick box like this, it asks me if I wish to make all of these objects static. I say yes, and now all the children have been made static. Now what I've done by clicking that tick box is I've made it static with respect to all of the different subsystems. So this will be seen as static by the light map compiler, it will be seen as static by Unity's occlusion culling system, and so on. And this is generally, as a general rule of thumb, this is what you want anyway. Generally, if something is static, it doesn't move. It means it doesn't move with respect to any of the subsystems. So we can just click that tick box and assign it like so. But if you do find a case where you may want it to be only navigation static and perhaps not considered static by the occlusion system or the light mapping system, like I said, you just drop down that box and click the flag that you want. Okay, so if I click next the decals, we can see that the decals are these kind of posters and sprites on the wall. Can't really see them at the moment with the lighting. You can see one there with the blue outline. And these really have no depth to them for the most part, and we can see that they wouldn't really influence the nav mesh in any way, so we're not going to make those static. We'll leave them as they are. Next we've got the ground. Now we definitely want the ground to be navigation static. In fact, in this particular example, the ground polygon is going to be sort of forming the main part of the navigation mesh. So let's set that to static too, and once again agree to make all of its children static. We also have this lift shaft over here. We're going to make that static as well, because we can see that there are some pillars and the floor that form part of geometry that we don't want the player to ignore, or sorry, not the player, we don't want the navigation agent to ignore when it's plotting its routes. So we'll set that as static. Props, yep, things like these barrels, once again, we don't want our agents ignoring these and walking through them, so we'll set those to static. Wall boundaries, yeah, we definitely want the walls to be factored in to navigation mesh generation, and these inner walls as well. Now here's one that we don't really want in as part of the navigation mesh, I don't think, but it's up to you. They're these telegraph wires. Now there is an argument to be made, I suppose, for the fact that these wires, while up in the air, of course, do not in any way influence the way that our agent will navigate. We do have the wires coming down the side here, and therefore we wouldn't really want the agent walking through these. But having said that, the agent's not going to walk through there anyway, because this area is all generally blocked by the debris and the props, things like these sacks and these crates. So I'm going to leave these out of navigation mesh compilation. Then we have the battle bus over here. Yep, we want that to be static. We definitely want to carve that area out of the nav mesh. Otherwise, we're going to have agents just walking straight through the bus, and that would not look good. And the rest is just the main camera and a directional light, which has absolutely nothing to do with navigation mesh generation whatsoever. So what I'm going to do now is I'm going to go back to the navigation tab, and without adjusting any of these settings, because we're going to come back and look at these in a moment, I'm going to press the bake button. Hey, look at that. We have now had a navigation mesh generated. Now if we go back to the hierarchy view and we turn off all of the objects in our navigation scene geometry and then flick back to the navigation tab, we can see just the navigation mesh, and you can see this is the exact shape of our level, with all of the non-traversable areas of the walls and the battle bus down the middle here cut out of the mesh. But of course it's a much lower poly representation, which means it's much quicker to traverse. I'm going to go back to the hierarchy view and I'm going to turn back on our geometry. And finally, before moving on, you may have just noticed that the navigation mesh is only rendered in the scene view whilst the navigation window has focus. So you can see, for example, were I to select my hierarchy view, thus hiding the navigation window, the nav mesh is no longer rendered in the scene view. If I select the navigation tab again, the window has focus again, and once again the nav mesh is rendered. But even with the navigation window active, we can still control whether the nav mesh is rendered in the scene view by using the nav mesh display overlay, which is displayed in the bottom right corner of the scene view. And you'll notice that it has this show nav mesh tick box, which allows us to toggle on and off the rendering of the nav mesh. And if you're wondering what the show height mesh tick box does, the answer is absolutely nothing, at least at the moment. And that's because we haven't generated a height mesh yet, but we'll talk more about this in a moment. And finally, you may find yourself in a situation if, for example, your Unity workspace was laid out like ours is here, where you find yourself in a situation where you want the hierarchy view to be active so that you can select objects, but you would also like to have the navigation mesh rendered in the scene view. But that's no problem. All we have to do is simply drag the navigation window somewhere else, dock it, in this example, to the opposite side of the screen, and then we have both the navigation window and a hierarchy window, both with focus at the same time, and thus we get object selection and also the nav mesh rendering happening for us. In fact, I'm going to leave the navigation window on the right hand side of the screen for now while I talk about the properties of the Bake tab. So let me start this discussion by saying that in Unity's navigation system, each agent is actually represented internally as a cylinder with a radius and a height. And in fact, later when we create a nav mesh agent, you're actually going to see the cylinder drawn in the scene view. Also, you can see that the agent radius and the agent height are the first two properties that we can set when configuring nav mesh generation. Now, it turns out that treating the agent as a volume, such as a cylinder, with a height and a radius, is actually much more computationally expensive than if we were to just treat the agent as a single point in space. Therefore, that's exactly what Unity's system does to make its pathfinding more efficient. And of course, this is very important because we want it to be efficient. We want to be able to have lots and lots of nav agents all roaming our level at the same time. So what it does is it treats the nav agent as a single point in space. It assumes it's the center point of the cylinder that we define. But then what it does to counteract this is it moves the edges of the polygons away from the walls and other obstacles by that radius amount. And of course, this is equivalent. What I mean is, if we just zoom down here a minute and look at how far the nav mesh is away from the actual wall, you'll find that this is the actual distance of 0.5 meter, which is what we specified here when we baked the nav mesh. So if we were to imagine that our nav agent was a cylinder with a 0.5 meter radius, then when its center point was right on the edge of this polygon, the outer skin of the cylinder would indeed just be making contact with the wall. And with respect to the agent's height, the same is also true. What I mean is the agent height that we specify in the Bake tab, and in our example we used an agent height of 2 meters, is also factored into the navigation mesh generation process. So if we have a little look at how that works, if we go over here to this lift shaft, we can see that if we step inside the lift, we can see that a polygon has been created on the nav mesh that represents the floor of the elevator shaft, and its edges are indeed offset by the radius amount. But you'll also notice that this polygon, even though it's part of the nav mesh, it isn't actually connected to the main part of the nav mesh. There is no blue polygon indicating connectivity here. And the reason why this is because during the navigation mesh building process, it was able to ascertain that this beam, this horizontal beam here, is lower to the ground than 2 meters, and therefore it was able to determine that an agent of 2 meters would not be able to fit under that gap, and therefore would not be able to navigate from the main nav mesh onto this piece of the nav mesh here that is inside the elevator. Now you may find it weird it's bothered generating a polygon inside an area that we can't get to, and in fact if you look around the level you'll notice there's lots of polygons on top of buildings and On top of the battle bus here, we can see 2 polygons of the nav mesh, which once again are not connected to the main nav mesh, and therefore under normal circumstances a nav agent wouldn't be able to reach that or pathfind across that from the main nav mesh. So they seem wasteful. Well, first of all, it's a bit of a byproduct of the navigation mesh building process, but also it is useful, and that's because later on we're going to see that there's a thing called an off-mesh link that we can use in Unity to connect 2 disjoint parts of a nav mesh together. So for example, we could create an off-mesh link that teleported the agent from the floor nav mesh up on top of the bus and then back down onto the floor again. And because an off-mesh link has connected this to the nav mesh, it means that this polygon would actually be factored in as part of the pathfinding process. A path search could actually determine that the shortest path from the left side of the screen here to the right side of the screen is to actually go in a straight line and jump over the battle bus. So the next thing we're going to look at is the max slope, which is set to 45 degrees by default. Now, when the polygons, or at least the static polygons of our level, are analysed by the navmesh baker, it rejects any polygons that are not traversable. And one of the main things it uses for that is the slope of the polygon with respect to the ground plane. And here you can see that we've configured the navmesh generator such that any polygon that is deviated from the ground plane 45 degrees or more is considered to be either a slope that's too steep for the agents to traverse or a wall, for example. I mean, the most obvious example of this is actually a wall, which is obviously deviant 90 degrees from the ground plane. So why not just leave this at 45 degrees? Well, because that might not be what you need in your game. I mean, there's certainly levels in a Dead Earth city scene, for example, where we have some quite steep hills that the player is able to get up, and we should allow the nav agents to chase you up those hills. And in those cases, I think we had to sort of put it up to more like 50 degrees or 55 degrees. So you just have that flexibility there where you can really configure what sort of slope your agents are supposed to be able to go up. Next up, we have the step height. And this is necessary to allow us to configure the nav mesh generation process such that it allows our agents to be able to traverse flights of stairs or even smaller obstacles such as a tiny box, a tin can, a bit of debris that we wouldn't expect the agent to have to find a path around, but would expect them to simply step over. If we think about a flight of stairs, for example, the front-facing polygon of each step is actually at 90 degrees to the ground plane, so would be filtered out by the process. This would leave just the up-facing polygons of each step disjoint from one another and the ground plane. There would be no connectivity between them, and therefore the agent would be unable to find its way up to those individual polygons. Now, what the step height does is it allows us to instruct the navmesh generator and say that if there are any polygons like these disjoint step polygons that are close enough in height such that they're under a certain threshold, in our case 0.4 meters, then suck them in as if they're part of the nav mesh. Make them part of what the nav mesh is built from. So to see an example of that, let me just fly around to where these tires are here. Now, it's hard for me to get an idea of how big these are until we have a character in the scene, but I'm guessing these are pretty big, because even with a 0.4 step height, that's that's been excluded from the nav mesh. But let's see what happens now if I was to put that step height up to 0.5. So you can see if you look in the diagram at the top of the inspector for the bake tab, you can see this is a pretty high step height. This is like being able to walk up a step that comes up to your neck. Now see what happens if I bake this now. There you go. Kind of weird to look at, isn't it? But what would happen now is if we had some waypoint that we placed at the top of these tires, the nav agent would actually think that it could walk up this slope onto these tires and essentially just walk right over the top of them. And of course, this is very similar to how a flight of stairs would work, providing that each step isn't too steep such that the height is over this step height threshold. You're going to see like a ramp up those steps be created by the navigation mesh generator. Okay, so let me just reset that a minute and put it back to 0.4. So everything is looking fine and dandy at the moment, but let's talk about one of the really big downsides currently that Unity's navigation system has, and that comes from the fact that by baking the agent radius and the agent height into the nav mesh at development time, we have a real problem at runtime when we wish to represent agents of varying different dimensions. It's quite common in an RPG game, for example, that you're not going to be able to get all of your agents to fit within a humanoid cylinder. You might want to represent animals such as elephants. You might want to represent a troll that's 3 times bigger than a human. And you're going to have a real problem getting those units to work nicely with a navigation mesh that's baked to a standard humanoid form. For example, let's imagine we had a troll, for example, that was twice the size of a human. Therefore, it had an agent radius at runtime of 1 meter instead of 0.5. Using this navigation mesh, its center point would be allowed to go right up to the edge of this nav polygon. Now, in the case of a humanoid, its outer skin would be 0.5 meter away, exactly where that wall is, so all would be fine. In the case of the troll, however, its outer skin might be 1 meter away and would appear to be sticking or protruding through that wall. Now, there's not a lot we can do about this, except just try our best to get a nav mesh that fits all of our unit types. But you might be thinking, hey, no problem, what I'll do is I'll just generate multiple navigation meshes. One navigation mesh may be baked for my large characters, one for my small characters, and one for my medium characters. But unfortunately, you can't do that in Unity. Currently, we can only have one nav mesh baked per scene. Now, in Dead Earth, we may find down the road that we want to create some really badass end-of-level zombie that's like 3 times bigger than the standard humanoid zombie. And we're going to have a hard job getting that to navigate properly using this nav mesh. We may see it try to walk through doors that we can visually see it wouldn't be able to fit through, but it will sort of walk through those doors, and you'd see its body pass through the walls because the actual navigation system is still going to be thinking that troll is only 0.5 meter wide. Troll. I said troll. I mean that end-of-level zombie is only 0.5 meter wide. So there may be times down the road where for special units like that we have to use some of that knowledge that we learnt about in the last 2 lessons, the A-star pathfinding algorithm, and generate our own system to cater for these special situations. The next 2 settings I want to talk about are the drop height and the jump distance, which are under the section in the bake window called generated off-mesh links. Now, we touched upon off-mesh links a moment ago, and I explained them as a manual thing that we usually create to connect disjoint parts of the nav mesh together so that we can have an agent traverse from one polygon to another in the nav mesh, even if there is no connectivity between them. Now, in the case of the drop height, what we're basically saying is, let's imagine that we have a small ledge in our level, and we would generally expect this to be the type of ledge that not only the player would jump off and survive without any problem, but we'd also expect our agents to be able to jump off of that ledge as well. But of course, the polygons at the top of the ledge and the polygons at the bottom of the ledge would not be connected. Therefore, the agent wouldn't be able to ascertain during a path search that it is able to move from the upper polygon to the lower polygon. However, using the drop height, we can say that if 2 polygons are disjoint in the y-axis by a height that is less than this drop height threshold, then assume that they are connected, create off-mesh links for us, and allow paths to be plotted over those disjoint polygons, and furthermore, let the agent follow that path so that it can traverse from one polygon to the next. And the jump distance is the same. If we imagine, for example, that we had a city in our game that had had an earthquake, and let's imagine that right down the middle of the high street there was a massive crack in the road. Well, I say a massive crack, let's say it was a tiny crack, let's say it was just 0.5 meter wide. Now, the polygons on the left and right sides of the crack belonging to the nav mesh would be disconnected, and therefore there wouldn't, under normal circumstances, be any connectivity between them. But we would be able to see in the game. It would look really lame if we have a zombie chasing us and then we jump over this little crack in the road, and then the zombie stops and then runs off in the opposite direction, trying to find the long way around so it doesn't have to jump over this little crack. We are going to come back to off-mesh links later on in much more detail when we find that we have to generate them ourselves for very special cases, but I don't want to sort of muddle this lesson with a discussion of something we're not going to use for quite a long time. What I want to talk about now is the advanced section, which has a manual voxel size setting, a min region area setting, and a height mesh setting. Now, the height mesh is very important in a game such as ours, as you're going to see in a minute that the nav mesh that is generated only really very loosely hugs the contours of the polygons for which it was generated, and this is seen very clearly on a terrain where the nav mesh may actually hover quite some distance above the terrain or below the terrain in certain cases. And when that's the case, because our agents are obviously walking on the nav mesh, it can really be visible that our characters look like they're floating above the ground. And the height mesh is a way for us to store more accurate data along the y-axis so that we don't have this problem. But to understand why this is all needed, we need to understand a little bit, and I mean from a very high level, how a nav mesh is built. And I'm going to visit a website called www.critterai.org to help me with my discussion. Now, you really want to visit this website if you are at all interested in the nuts and bolts of nav mesh generation. This guy has generated his own navigation mesh generator. It comes with API documentation and you can download the source code, so it's well worth a visit. I'm going to peruse this site and use some of his diagrams to help me with my much lesser detailed discussion. Okay, so you might be forgiven for thinking at first that in order to generate a nav mesh, we might start by picking some polygon in our level and then simply performing a flood fill out from there, visiting neighboring polygons, and simply collect the polygons that are traversable and reject any that we find that are non-traversable, perhaps because their incline is steep compared to that of the ground plane. But it doesn't work like that at all. The problem is that a game level these days is usually comprised of hundreds if not thousands of separate distinct meshes that have no connectivity at all. We also need to build it in such a way that we cater for the ability to have those disjoint polygons in the nav mesh that we were talking about a moment ago, so that we can create off-mesh links between them if we desire. And we also need to do it in such a way that supports multi-leveled overlapping nav meshes, so that we could, for example, generate a nav mesh for a block of flats. What actually happens is the original polygons are sent into a voxelization process that builds a very coarse representation of the world out of cubes. Those cubes are then later used to build the final polygons that are output. So the polygons that come back to us are often very, very different to the ones that we input. In order to understand the voxelization process, let's use an example that we're already quite familiar with, that of drawing a perfectly diagonal line on a computer monitor display. Now, a computer cannot draw a perfectly diagonal line on a computer monitor display. The monitor display itself is just a grid of squares. Each square is called a pixel. Therefore, if we draw a line, we have to get as close as we can by coloring in those square pixels. In fact, what we do is we find the pixels that the perfect representation of the line would pass through and color them accordingly. On the screen, we can see what a diagonal line might look like in a very low resolution display. The voxelization process is essentially the 3D version of this. Instead of the screen being divided up into a grid of pixels, the world is divided up into a grid of cubes. Each cube is called a voxel, and there could be millions of them. The name voxel, by the way, comes from the term volumetric pixel. The idea is that what we want to do is we want to test each of our polygons against the voxels. For any voxel that is found to contain a solid polygon, and in this instance we're referring to a solid polygon as one that is non-traversable, such as a polygon that has a steep incline with respect to the ground plane, then any voxels that that polygon intersects are marked as solid. What we're trying to do is find neighboring voxels in the same column so that we can represent them as a single span. In this diagram, you can see that in the central column, two voxels were found to be containing solid polygons, and therefore we have a span that is 2 voxels high. When this process has been completed for all the polygons and all the columns, what we end up with is a cuboid representation of the original geometry. To use something a bit more familiar, it might look a little bit more like a Minecraft world. Of course, the voxels are normally a great deal smaller and more high resolution than this, so it's never quite like that, but the general premise is the same. Of course, this voxel representation currently tells us the solid spans. What we're more interested in is the empty space, the space between the solid spans that our agents can traverse. In this diagram, we can see that the yellow areas represent the spaces between two solid spans. They are the open spans, as they're called by this process. What we're trying to find is the floor and the ceiling of each open span for any given column. The floor of an open span is simply the uppermost polygon of the solid span that is immediately beneath it. The ceiling of an open span is simply the bottom polygon of a solid span that is immediately above it. Once we have all the open spans, we have a diagram that looks like this on the screen. The red squares show the floor of each open span, the green squares the ceiling of each open span. As we know the heights of each open span at this point, a further rejection process takes place where we reject any open spans that are not high enough to accommodate the agent height that we set in the navigation mesh bake settings. Now it's time to gather up all of the floor pieces of neighboring spans and try and consolidate them into continuous regions. Some margin for error is allowed based on the settings so that it doesn't just apply to floor pieces that are exactly coplanar, but ones that have a degree of error that fall within the threshold. In this example, we can see that the floor of 4 neighboring spans meet at a corner point that has 4 different vertex positions, one for each span of a differing height. In this particular case, usually the highest vertex is selected and used as the vertex in the mesh for all of those spans. What we're trying to do here is create simple polygons from those span floors. Eventually, when the regions have been created, we divide those regions up into convex polygons and store the result as a graph and as our nav mesh. So then, because the input polygons are essentially snapped to a voxel grid, we can imagine how in a scene that has a high degree of topology variance, such as one with a terrain, how the resulting nav mesh is going to only be at best a very loose fit over those terrain polygons. And in many cases you'll see, if you walk around a terrain scene, you'll see the nav mesh is rendered way above the terrain polygons. And of course the problem being is that the agents themselves walk on the nav mesh surface, not the underlying terrain surface. So to us they will look like they are hovering in the air. Fortunately, this can be resolved by generating a height mesh at the cost, of course, of extra memory. So to demonstrate this, let's go back over to those tires that we looked at earlier. Now, in the default settings, we can see that this is considered too high a step. Therefore, this whole area is ruled out as too high for an agent to navigate. But if we ramp up the step height once again to 1.5 meters, and bake the nav mesh again, we can see that now this has been included into the nav mesh, and the nav mesh has been altered such that an agent can walk up onto that first set of tires, and possibly even the second set. The problem is though, we can see already how loosely fitting that nav mesh is. Were an agent to be stopped while it was traversing this slope, such that it was halfway up the slope, it would indeed have its feet hovering in mid-air. Now, this inaccuracy is only really an issue in the y-axis, where we want to see our characters grounded. So what Unity allows you to do is to generate a height mesh which will separately record the actual heights that an agent should be at to match the underlying polygons, or at least to hug them much more closely. So let's see what happens if I click the height mesh, tick box, and then click bake. The height mesh will show up as a pinky purpley structure here in the scene view. So if I turn off the nav mesh, we're left with just the height mesh data, and as you can see, the height mesh correctly hugs the floor polygons and the tire polygons right up to the point where that stack of tires begins, and then jumps up onto the tire's upper surface. So when we're using the nav mesh and our height mesh, we're still using the nav mesh to know where we can go on the XZ plane, which areas are accessible, but the height mesh is used to adjust the altitude of the agent such that it sits on the floor properly, or at least much more closely. Okay, so I'm going to reset the step height back to 0.4. I'm going to turn off the height mesh for now, and I'm going to rebake, so we're back where we started. Okay, so looking at the other settings under advanced, we can also see that the voxel size is currently set to 0.166. That basically gives us a voxel size of 3 voxels per agent radius. In other words, 3 of those cubes fit into our half-meter radius. Now, I usually find that Unity's default settings are absolutely fine, but if you do find you need more resolution, we can override the voxel size by clicking the manual voxel size tick box, and then we can compute which voxel size we wish to use ourselves. Of course, the more voxels we use, the much longer it's going to take to generate the nav mesh, and there is also the possibility that we're going to generate a more detailed nav mesh with more polygons, which is going to be slower to traverse when doing path searches. Of course, we could go the other way and we could reduce the voxel size. We have to be careful when we do this, though, that we don't make the voxels so big that an entranceway such as this is now encompassed by a single voxel. Let me show you what I mean. I'm going to change the voxel size temporarily to 1.5 and press bake again. As you can see, actually, that's a bad example. Let me set it to 1.1. There you go, that's a better example. So in this example, we can see that a voxel is obviously so large that this spans the entire entranceway, in which case this voxel here does contain solid geometry, both of the left wall and the right wall. And as we saw when we were looking at the nav mesh generation process a moment ago, if any voxel is found to contain any solid geometry, it's marked as a solid, non-traversable voxel, and therefore these 2 rooms are no longer connected. You have to be careful with that. So I'm going to put that back to the default voxel size and rebake again. And like I said, the default settings normally work fine for me. Oh, and just quickly, if I was to select the Object tab in the navigation window, we can see how this can be used to configure the navigation mesh generation settings on a per object basis. So were I to select the battle bus here, we can see that from here we can set whether it's navigation static or not. Obviously, if it's not navigation static, it means it doesn't get included into the nav mesh generation process at all. And this is just another way of doing what we did earlier when we did it from the inspector, like so. Just gives us another way to turn that on and off for any given object. Now the other 2 settings, especially the navigation area, I'm going to add a cylinder to the scene that's going to better make my point. Okay, so first of all, let's imagine that we have this piece of geometry in our scene, and let's say that it has a texture map to it of like a fire pit, or we've got some particles in there that make it look like a fire. Now we can see that if I was to set that as navigation static and then bake the nav mesh, the step up onto that cylinder is so small that the navigation mesh does indeed walk right over the top of it, and our agents would walk over that cylinder no problem at all. But if it was, say for example, fire, we might not want them to walk through that. So one of the things that we could do is we could set that to the not walkable area. Remember, on the areas tab there are 3 built-in area types: walkable, not walkable, and jump. And also you can create a whole load of custom walkable types, which we'll do in a moment. And you can see that each of these types has a cost associated with it. So for the not walkable type, go back to the Object tab and click Bake, you can see that because this has been marked as not walkable, the nav mesh has been carved around the outside of it. So even if we turned that off now, if we didn't need it in our scene anymore, the hole is still left from where it was before. And that would mean that if we were stood on one side of the fire pit and the agent was stood on the other side of the fire pit, it wouldn't do anything daft like walk through the fire pit and come after us. Of course, there's other things that we can do that aren't quite as severe as that. If I put it back to the walkable area and I turn my cylinder back on again and bake the nav mesh again, just to see it's included in the nav mesh. One of the other things that we could do is we could say, well, instead of this being a fire pit, let's pretend it's a pond. It's full of water. In the case of a shallow pond like this, the agent would be able to walk through the pond, but it wouldn't be its first choice. It would definitely walk around the pond and stop getting wet if it could. But what happens then if, for whatever reason the areas around the outside of the pond were to get blocked off by debris or something like that, and then the only way that the agent could get to you would be to walk through the pond. It would be stupid in that case if it didn't make a path through the pond towards you, as that was the only route. So what we could do is we could go to the Areas tab and we could create a new navigation area and call it Water. And we can say that our agents really don't want to walk through water unless there's no choice. So we'll give that a multiplying cost of 5, okay? So any path that goes through that pond, while it's going through that pond, it's going to be as if it's 5 times longer. And therefore, during the search, this is not going to seem like the quickest way to get from one side of the pond to the other. So if I bake that again, not that we should see any difference, everything looks fine. The pond is still traversable, but if we had an agent on one side of the pond and told it to walk on the other side of the pond, it would actually calculate a cheaper route is by walking around the pond. And that's what we'd want. We'd want the agent to walk around the pond unless he had some specific reason to walk through it. But like I said, if we were then to place obstructions either side of the pond so there was no path around the outside of the pond, well then the agent would say, hey, this might be an expensive cost walking through the pond, but it is still a viable path, so I'm going to pursue the player by walking straight through the pond. So I'm just going to get rid of the cylinder and return our level back to how it was before. So it's worth pointing out at this point that it's the actual polygon data that is used to generate the nav mesh, not the colliders of the scene. This scene, for example, has no colliders, and even if it did, they would be ignored by the navigation mesh generation process. However, what I want to do now is add some colliders to this scene so that when I add my waypoints to the scene in a minute, I can have them easily snap to the floor plane. Now, I could just go through all of the objects in the scene and add individual colliders to them, but fortunately I don't have to, because this level also comes with a custom-made low-poly collision mesh that I can use. So what I'm going to do is I'm going to find where that is first of all. I think if you go to the project view, open up the navigation example folder, open up the source folder, open up the models folder, and then open up the collision meshes folder, you'll see there is a mesh in there called env stealth collision. And if I select that and make sure I have the inspector selected on the right hand side, we can see what that mesh looks like. And as you can see, the reason why this is so efficient to be used as a mesh collider is in areas such as here, where there were piles of debris and barrels and pallets and sandbags, they would all have to have individual colliders added to them. Whereas in the collision mesh, we've simply just used a few polygons to build a wall around that area. And this happens in a lot of places. So we end up with a single collision mesh with very few polygons. So it's very efficient for the collision system to use. So in order to use this for the collision data for our scene, all we have to do is select our navigation example geometry game object. That's the parent object of our hierarchy at the moment. And then in its inspector, click the add component button, type mesh, and then choose to add a mesh collider. Now what we've done at this point is we've added an empty mesh collider. It actually has no mesh data. We're going to have to assign that. And we do that quite easily by, in the project view, opening up the collision mesh so that we can see its underlying mesh data. And then we drag the reference of that mesh data and drop it into our mesh collider. And now you can see, if you look in the scene view, the green outlines do indeed show that we now have this mesh collider in our scene. And you can see what I mean here, how this area here with the 3 barrels, the sandbags, and these various pallets and other props would all have to have individual colliders added to them, whereas what this mesh collider does is simply just builds a wall around those areas, which means there's much fewer polygons added to the collision system. So that's pretty cool. Just to prove what I just said is true, if I select the navigation window and hit the bake button, you can see that the navigation mesh is exactly the same. It hasn't been changed by the inclusion of that mesh collider. In fact, if you want to make totally sure that that's the case, then if I actually set all of our objects to not be static, so they're not included in the nav mesh generation process, all we have at this point is a load of dynamic objects and of course that mesh collider. And if I bake the nav mesh now, nothing gets created. In other words, that mesh collider is completely ignored, and because all of the other objects are now dynamic, they're not navigation static, their polygons are not being included in the navigation mesh generation process. So that's pretty conclusive. So what I'm going to do now is, with the inspector selected, I'm going to reset those objects that we need set back to being static, so they are included. It was the decals and the wires, wasn't it, that wasn't included. Put those back to static again. Generate the nav mesh. Finally, it is also quite common that game companies will custom build their own navigation meshes. The reason why you might do this is because you might not be happy with the navigation mesh that Unity is generating for you, and you might get a more exact navigation mesh, one that fits your needs properly, if you have it actually hand built by the artists. I believe they did this in Skyrim. They had teams and teams of modelers creating all of the individual nav meshes for each section of the world. So how would we do something like that in Unity? Well, we're going to use that collision mesh as an example. So in order to demonstrate this, I'm going to clear the current nav mesh. I'm going to set all of our objects to be non-static, which means that if we were to bake the nav mesh now, as you can see, no nav mesh would be baked. So what we would do in this particular case is we can't rely on the mesh collider we just created to influence nav mesh generation in any way. But what we do know is that that collision mesh is also a mesh in its own right, made of polygons. If we drag it into the scene and then turn off our original geometry, you can see what I mean. So because we now have a copy of this collision mesh in the scene with actual polygon data, we can set that as being a static object so that it's included in nav mesh generation. Click bake, and there you go. We've now just baked a custom navigation mesh. We've influenced navigation mesh generation by using custom geometry, not the actual visible geometry that we're going to use. So at that point, of course, we can delete that copy of the collision geometry that we used purely for navigation mesh generation. The nav mesh still remains, and then re-enable our original geometry. And there we have it. We have the original geometry and we have the navigation mesh generated from the collision geometry. So that's pretty cool. Okay, so I'm just going to reset all that now because I don't want to use that nav mesh. That was just an example. So once again, I'm going to reset all of these objects to static. I'm going to make dynamic the wires and the decals. Oh, and the camera and the light, although it doesn't really make a difference. And then I'm going to go back to the navigation view. I'm going to clear the navigation mesh that we baked using that collision geometry, and I'm going to bake using the regular geometry again, and we're right back where we started. So we've seen something pretty interesting there, right? We've seen how to use a custom collision mesh. And we've also seen how to use a custom nav mesh, or at least custom geometry to influence how a nav mesh is baked. Okay, so next up it's time to start adding some waypoints to our scene. So the first thing we're going to want to add is just an empty game object that can act as a parent container. So if you go to the game object menu and then choose create empty, I want you to left click once and rename this waypoints. Now, because this is going to be the parent object of all our various waypoints, we want to make sure that we position this at 0, 0, 0 in the world. And we can do that by, with the waypoints game object selected, going over to its transform, left clicking on the little cog on the right hand side of the transform component and clicking reset. And as you can see, this is set position and rotation to 0, 0, 0 and the scale to 1, 1, 1. Now the reason I always do this with parent container game objects is because it wouldn't be the first time that I've left the container at some random position in the world and made no note of where it was. And then I add all of the children to it, position them meticulously exactly where I want them, and then due to some accident I accidentally drag the parent container to some completely random place in the world, which of course moves all of its children along with it, all of my waypoints. And then I don't know where the parent was ever supposed to be in the first place, and I have to replace all of my waypoints again. Now, of course, you could just say, well, why don't you just press undo? which I would do in that particular example, but I often don't recognize that I've done these things until days later when I start working on the waypoints again, and then there's nothing in the undo buffer to undo. So with our waypoints container at 0, 0, 0, we want to create our first waypoint. So the way we're going to do that is with the waypoints game object selected, go to the game object menu and do create empty child. This is going to create a child game object of waypoints, and we're going to call this waypoint 1. Let's just put that somewhere where we can see it. Now, obviously, when we've laid down loads of waypoints, we're not going to be able to see them, so we want them to show up visually in the scene view. So the first thing we can do is we can use that little flag graphic that we imported in the gizmos folder. Just to remind yourself, we copied this to the deader folder. As you can see, it's this graphic here. Now, it's going to look different to that because it's got a transparent background, which isn't showing up here. So how do we make our waypoint game objects render this in the scene view? Well, with the waypoint 1 selected, I want you to click on the cube right in the top left corner of the game objects inspector. And here's where we can choose the icon that is used to display this in the scene view. So, for example, if you look in the scene view, I can choose, there are different sort of label colors that I can choose. But what I'm going to do is I'm going to choose other. And that's going to give me access to all of the textures that I've got in my project. And here is our waypoint texture. Of course, you could, if you've got more textures than me, because this is a pretty small project, you could just type in way, and that will do a search for the actual waypoint texture. Okay, so look at our waypoint now. It now shows up as a little flag. Now, because we added a collider to our scene, that means we can now snap that to the floor by holding Control and Shift, and then just moving that anywhere will snap it to the surface that is immediately underneath it. So there you go. So where shall I put the first waypoint? I think I'm going to put the first waypoint in this room here. Want to create a second waypoint, all I have to do is just duplicate waypoint 1. So select it in the hierarchy view, edit menu, duplicate, and then hold in a Control and Shift again, I move that and put it in the second room. You can also see what's really cool about Unity is it's automatically renamed the next waypoint using the same naming mechanism, so it's called it waypoint 2. Just make sure I position that in the middle of the room. I'm going to duplicate that one again. From now on, I'm going to press just Control D, okay, to speed things up. And I'm going to put this waypoint in this room here. Duplicate again. Duplicate again. Where should I put the next one? What about right in front of the elevator shaft? One more. Put that in there. There you go. So now just by looking at the scene view, we can see that there are our waypoints. But I want to actually make my scene view render better than this, and in a minute we're going to write an editor script that's going to connect them with lines so we can see exactly which waypoint it is in our waypoint network. So that's the waypoints created, but what we want to do now is we want to create some object that can contain a list of all these waypoints in very specific order. I call this a waypoint network. Now this is just going to be another game object that's going to have a list as a container, a generic list, that can just store the waypoints in the sequence that we want them to be in. Let's do that now. Let's go to the game object menu, create empty, reset the transform, so once again it's 0, 0, 0 in the world for exactly the same reasons, and we're going to rename this waypoint network 1. Now the reason I call this waypoint network 1 is we might have multiple waypoint networks but all using the same pool of waypoints. For example, the first waypoint network, we may just add the waypoints in the exact order in which they're listed here, 1, 2, 3, 4, 5, 6. But we then might create another waypoint network which has the waypoints added in reverse order or in some completely random order, such as 1, 3, 2, 6, 5, 4. And of course, we may create a waypoint network which contains just only a few of those waypoints. Now, when we create an agent, we'll be able to assign a very specific waypoint network to that agent. So we can have multiple agents in the scene, all following different waypoint networks, but all comprised from the same pool of waypoints. Okay, so now it's time to write our first script. So I want you to go to the Dead Earth folder. I want you to open up the scripts folder, and with the scripts folder selected, I want you to right click and do create C# script. And we're going to call this AI Waypoint Network. With that script selected, I want you to drag and drop this onto the game object called Waypoint Network 1. Now obviously this script doesn't do anything at the moment, so let's open it up in MonoDevelop by double clicking on it, and we'll give it some functionality. Now the first thing I'm going to do is I'm going to delete the start and update functions. We don't need any of that boilerplate stuff. In fact, this class isn't actually going to have any functions at all. It's literally just going to hold a public list. Now I want to store my waypoints in a generic list, so we're going to need to include the systems.collection.generic namespace. So what we're going to do is we're going to create a public list, and the type of object that our list is going to hold is going to be references to transforms. We don't really need to store the actual game object. It's only the transform of each waypoint we're interested in, and more particular the position of the transform. Actually, as that's a public variable, I will make that a capital. And that, believe it or not, is that script done. If we now save that off, not a script that's going to set the world on fire, is it? And then we select our Waypoint Network 1 game object, we can now see that in its inspector we now have this waypoints array that we can now add our waypoints to. So we want to add 6 waypoints to it. Set it to 6, and then we'll just drag over our waypoints into that list. For now we'll just copy them over in the exact order. I mean, you don't have to, you can put them in any order you want, it doesn't matter. It's just going to control the order in which our nav agent is going to visit each waypoint. So we now have Waypoint Network 1. But what we could do now is create another waypoint network simply by duplicating that one, calling it Waypoint Network 2. And what we could do is we could change the order around of those waypoints. So we could have waypoint 2, waypoint 6, waypoint 5, waypoint 1, waypoint 3. I don't even know what that's going to look like. And waypoint 4. So we've got 2 different patrol routes now with those 2 different waypoint networks that we can assign to our agents. And this is just, it looks so much better than having all of your agents patrolling the same waypoints in exactly the same order, because what we're trying to do is we're trying to make it look to the user as if our agents aren't following waypoints at all. We want them to appear to be sort of patrolling randomly as a human would. So the more waypoint networks we have, the more choice we have with respect to assigning different routes to our agents. Now, despite the list of tasks I intended to get done in this video, I've just looked at the time, we're at the hour mark and I'm not even remotely done. So I'm going to have to roll this into the next video, okay? So when we come back in the next video, we're going to write a custom editor script that's going to allow us to do a custom render of our waypoint networks in the scene view. And we're also going to write our first agent behavior. This is going to be a script that is going to interface with Unity's NavMesh agent component and have our object traverse between the waypoints using the NavMesh and using Unity's navigation system. And we're also going to take a look at how we can use Unity's navigation obstacles. These are the things that allow us to deal with other dynamic objects that might be moving in the scene, because we don't want to walk into those either. And of course we need things like this to even deal with simple constructs such as doors that open and close. So sorry we didn't get everything I wanted to get done in this video, but don't worry, we'll do it in the next video, and I hope to see you then. Bye.